Modeling with exponential functions. So many real-world situations can be modeled using exponential functions. Some of these involved a quantity that's getting larger, and we call those exponential growth. So things that get larger exponentially, we call it exponential growth. And things that get smaller, actually, exponentially, we call exponential decay. Okay, so growth for getting bigger, decay for getting smaller. When using a table to represent an exponential function, we're going to see a constant ratio between the terms in adjacent rows. So that's where what we did in the video before, where we took the y value before it and divided it by the y value that came before it. Sorry, where we took a y value and we divided it by the y value that came before it, and we kept getting the same ratio all the way down. So that's what we're going to be seeing in a table of values. This ratio is the base of the power, and we talked about that in the last video as well. If the base is greater than 1, so if the bottom number is greater than 1, so if it looks something like this, 3 to the x, then that's going to be exponential growth. If it's 5 to the x, that's going to be exponential growth. And we're going to see this value when we take y2 and divide it by the y value that came before it. I'm going to zoom in just a little bit here. So when we take that y value and divide it by the y value that comes before it, when we get an answer, a numerical answer, that ratio is what we're finding. If that ratio is greater than 1, then we're going to get exponential growth. And if it's going to be less than 1, like let's say we figure out the ratio is going to be a half, then it's going to be exponential decay. It's going to get half and half and half and half and half again. So let's talk about an example where these two things might happen. Let's say that you have bacteria, and you're going to start off with 10 bacteria to begin with, but it's growing. It's growing by double every day. So at the very first day when we start, we don't put in a 1 for the first day. The very first day we call day 0. So it's the very, very first day. So it's not going to double at all. You're just going to have 10 of them, right? 2 to the 0 is 1, and you'll have 10 bacteria. But after the second day, or after the first full day goes through, that's going to be a 1 up there. And now you're going to have 20 bacteria, aren't you? And then after the next day, you're going to have 40 bacteria, because it's going to be 10 to the 2 to the 2. And the third day, the third full day that goes by, you're now going to have 80 bacteria, aren't you? And the next day, you're going to have, let's see, it's going to be 10, 2 to the 4. So it's 160 bacteria, and so on, until all of a sudden you're going to have so many bacteria. So it keeps doubling, right? So it started off pretty small. It started off with 10, then it went to 20, then it went to 40, then it went to 80, then it went to 160, then it went to 320, then it went to 640, then it went to 1,280, then 2,560, and you see that this is going bigger and bigger and bigger, but it's getting bigger faster, isn't it? It's getting bigger faster, and what's happening is we're getting this number of bacteria sort of starts off like this, but then it takes off like that, until all of a sudden there's like 10,000 bacteria, and that's like not a big deal, but then the next day, it's 20,000 bacteria. And the next day, it's 40,000 bacteria. And the next day, it's 80. Now, that's exponential growth. It just takes off. We hit that critical point where all of a sudden it matters and it's gone. Okay? And that's when your sandwich becomes fuzzy and green and stinks. And you have to throw out that Tupperware before your parents see it. You've all been there. I know you have. So what about something that gets smaller? Well, radioactive materials get smaller and smaller and smaller. And what happens is you have a material that's radioactive. And what that means, do you know what that means? It gives off energy. And that radioactive energy can be used for good things and it can be used for bad things. So it could give you cancer, right? We've heard about that, radioactive poisoning and stuff like that. It could make you sick. Or we could use it in the hospitals on our imaging devices and different things like that, and it can be used for good. So it's an energy, and we have to know about that energy. But as this energy comes out, you have to give up something. And what gives up is mass. So the amount of mass that's here, this energy comes out. So as the energy comes out, the mass decreases. It gets smaller, okay? So what happens is you get this radioactive compound, and it'll have a half-life. And maybe it's every year you'll have half of it remaining. So if you're working in a hospital and you have 60 milligrams of some radioactive isotope that you need to have to run the imaging system, the diagnostic CAT scan, let's say, okay? And if this has a half-life of every year, so every year there'll be half of it remaining, after 1 year there'll be 30 milligrams remaining. After the next year, there'll be 15 milligrams. After the next year, there'll be 7.5. After the next year, there'll be 3.25. Do you see how it's going half and half and half and half and half? And let's say I need a certain amount to run the machine. Well, if I start off with a really big amount, 30, then after half a year, I'll have 150 left. Like, that's a big drop, right? Right at the beginning. And then I'm going to be down to 275. And then I'm going to be down to half of that, which is 37.25. I don't know. I don't trust my numbers. I don't know. 75 divided by 2. 37.5. But you see what's happening. Half and half and half and half. And it doesn't matter how much you start with. So if I have a bucket of it, that's 300 milligrams, and I have a smaller bucket that's only 30 milligrams. They both decay half as much in the same time. So after 1 year, this one's going to be 150, this one's going to be 15. They both decay by the same amount. It doesn't matter how much you have. Okay? Only half of it will be remaining after that time. And that time that goes by is called its half-life. Half-life time. I can't spell. Half-life. Okay, and that's for something that has a half-life that goes down by 2. It might not be a half-life. It might be a third life. It might go down by thirds. It might go down by a quarter. It might go down by an eighth. But that's an idea of something that gets smaller and smaller and smaller. Okay, so we have exponential growth. We have exponential decay. And the really weird thing about exponential growth and decay, I have to be honest with you, is this is what nature likes. This is how nature grows. Population dynamics, the people on the planet, we're growing exponentially. Radioactive elements, they decay using exponential decay. Bacteria that grow, that we're able to use to check if you're sick. You know when they take you to the hospital to check for strep throat and they shove that gauze thing in your mouth at the back and they take it? What they do is they take it to a lab and they take that and they spread it on something called agar, which is basically bacteria food. And they take it and they put it and they let it grow. They take a microscope and they estimate how many bacteria there are in a certain area, and then they let it grow over a certain amount of time. And they take it back out and they do another count and they find out how much more bacteria. Then they let it grow a little bit and they take another count. And then what they do is they graph this. And they graph how quickly it's growing. And based on this value and based on how quickly it's growing, they know whether you have strep throat or not. They know whether you have a different type of sickness. That's how they figured that out. So exponential growth and decay is really important in the sciences. It's really important in life. So let's take a look at a little bit of it.